Happy Valentine's Day. We may in fact be serenaded at some point. That often happens in a large class like this. I'll be interested to see. So today we're going to put our finishing touches on our investigation in how to build combinational logic to implement, almost any sort of functionality that we want. So we talk about combinational logic as having a functional specification. And here we have a little word diagram that says, look, the description of this yellow box is that if the value of C is 1, we want the value of B to appear on the output Y. Otherwise, we want the value of A to appear on the output Y. And, words are not a very satisfactory description. We want to come up with perhaps slightly more engineering type of notation to describe the functionality. And once we have that notation, we'll work on turning that into an actual schematic diagram of combinational logic gates that, if we wire them all up correctly, we hope will implement the exact functionality that we want. So we're going to actually investigate sort of two alternatives today. The first is the truth table. The truth table is actually a very nice and straightforward approach to describing completely the functionality. And the nice thing about the truth table is that, for instance, here we have 3 inputs, all listed A, B, and C. And when we think of, and they're digital values, so each of the inputs can take on the value 0 and 1, and we've already talked about how to interpret voltages as digital values. And if we think about 3 inputs, each of which can be 0 and 1, how many possible combinations are there altogether? Well, there's 2 for A, and 2 for B, and 2 for C, and the values can be chosen independently. So there's 2 times 2 times 2, or 2 to the third, or 8 rows in the truth table. And the thing I like about the truth table is that once I list all the 8 possible combinations of the inputs, I can make sure I'm very clear about what the value is for each of the combinations. So the truth tables are sort of self-evidently exhaustive. In other words, I've completely specified the function. I haven't forgotten about one of the possible combinations and said, oh yeah, in that case I want. So in the truth table, I've resolved all of that. And you can see, in fact, that the only difference in the description, truth table description of 3 input functions, they all have the same set of combinations of the possible inputs. So there's 8 possible combinations of 3 inputs. And so different 3 input functions would differ only in the value I wrote in the output column. And so I've written a particular truth table here, which is in fact a translation of the English words. So when C is 1, you can see the output follows the B input. And when C is 0, you can see the output follows the A input. And so this is a different, sort of more straightforward, systematic way of describing the operation of a function. A second alternative is as a Boolean equation. And Boolean equations involve 3 operations that we're going to be looking at. So if we want to talk about A and B, we'll use the multiply notation. So this is A, this is AND. So we're going to use the word product to represent ANDs. And as often in mathematical notation, we're going to leave out the dot because it gets a little tedious. We can talk about A or B, and we're going to use the sum notation for that. So we're going to use this guy as the plus sign to represent ors. And then we can talk about not A, and we'll put a little bar over something. And in fact, we can put a bar over these 2 guys. For example, that would be not A and not B. And we have to be a little careful with our typography, because I could have also written this, which I would have called NAND, okay, which is the not of A and B. And so you can sort of see there's a distinction between whether there's a break in the bar or not, as to whether it applies to the whole product or whether it just applies to individual terms in the product. And you have to squint a little closely when you see a Boolean equation to make sure you understand what the bar is knotting, whether it's knotting a whole bunch of terms or whether it's knotting each individual term. And so you just have to make sure you understand how far the bar is stretching. So here's a design approach. Let's start by making a truth table, and you can see I've just copied the truth table from the previous page there. And then what I'm going to do is to write a product term, in other words, an AND of a bunch of the inputs for each of the ones in the output column. So here I have 4 ones in the output column, and I'm going to end up with 4 product terms. So this is what's called a sum of products notation. So y is 1. That's what I'm going to write an equation that describes when y is 1. And it's 1 in 4 different situations. So if I look at the first situation, it's 1 when c is 0, and b is 0, and a is 1. I mean, I just sort of read across here. And in terms of how I would write a logic expression, I would say not b, c, and not b, and a. Everybody sort of with me on that? So there's a very straightforward translation of, I just read across the rows, and every time I see a 0 on the input, I write not of that guy. So I see a 0 here, so I would write not C, and not B, and A. No, it's A. Okay, so this product term here describes one of the rows in the truth table where the output, we want the output to be 1. And similarly, we can write product terms for each of the ones. So how many product terms could I have at most? 8, right? Because there'd be, if I had an output column that was all ones, I would, with this very simplistic approach, write down a product term for each of the ones in the output column. Now, as it turns out, if all the outputs are 1, there was a simpler equation I could have written. I could have written y equals, 1, y equals true. And we're going to talk about simplification in a moment, but for now, let's stick with this sort of systematic approach. Okay, and if you say, okay, well, I have a sum of products, Chris, what does that get me? Why is that a sort of a nice idea? Well, I can very quickly derive a schematic diagram involving inverters and AND gates and OR gates from my sum of products expression, right? So what I've done is the product is represented by this giant OR gate, which will have as many inputs as there are product terms. Each of these AND gates represents one of the product terms, and then I've wired it up appropriately. So here, this is the product term that was A and B and C. This top one is the product term which was not C and not B and A. And you can see I've used inverters liberally to produce the not of B and the not of C whenever I need it. And so what we've done is we've gone through this sort of 3-step process of truth table to a sum of products Boolean expression to a schematic diagram. And we know from the previous lecture how to build each of these gates. If these were all inverting gates, we could just build them as individual CMOS gates. And if in a non-inverting logic, this positive logic like AND, we know we could build that as a CMOS NAND gate followed by an inverter. So we sort of have a strategy. It may not produce the most efficient circuit in the sense of being the smallest or the fastest, but it will produce a circuit whose function is correct. And now you can write down any truth table you want, and we have a mechanical way of producing the correct circuit diagram. We can think about the propagation delay through the circuit, and sort of naively you would say, well, there's some inverters I have to go through, and then on my path to the output, from any input to any output, I'm trying to think of what's the longest TPD. Well, I have to go through potentially an inverter, followed by a product term, followed by this OR gate. So that it looks like there's 3 things along any path, or at most 3 things along any path from inputs to outputs, and that suggests that I would have a fairly good TPD. The difficulty is that as the number of inputs to the ANDs and ORs grows, it turns out the gates get slower and slower and slower. And we'll talk a little bit about how to fix that up, or adjust our circuit diagram to take account of that here in the next couple of slides. Is everybody happy with this sort of sum of products notation? It's actually a very simple idea. Is there a difference in representation? The answer is yes. If we look closely at these symbols, and I admit this diagram is not quite as doesn't accentuate that as much as it can. An AND gate has the symbol, chalk please. So an AND gate has a symbol, so let's go back to this being AND. What you'll do is you'll find it has a straight back, okay, and then sort of a rounded front, like so. So that's an AND gate. An OR gate has a curved back and then sort of curved sides, like so. And in fact, that diagram is attempting to show that, although because of the way you can draw gates in PowerPoint, it's a little tedious and it doesn't quite show through. Everybody happy with that? Other questions about summer products? So you should be comfortable with either me giving you a truth table or a sum of products expression, or in fact any Boolean expression, or a schematic, and all those are representations of a particular function. The schematic is nice because we can go off and build it in the lab. So we've talked about AND gates and OR gates and inverters, you know, and we can, here I've listed the some various two-input functions, AND and OR, and NAND and NOR. We met NAND and NOR as CMOS gates in the previous lecture. You can see AND and OR are basically just inversions of those. Well, how many two-input gates are there? You know, is this, you know, I've listed 4. If I were going to list all the possible two-input gates, all the different logic functions, how many could I list? Well, notice, yes, 16, and in fact that's the correct answer. Let's do the counting to figure out how we got 16 as the number of possible two-input Boolean functions. And you notice that, of course, the enumeration of all the possible value of the inputs is the same. It's the same 4 rows. Right? What differs between one function and the next is how I fill in the output column. And I can put a 0 or a 1 for the first row, and a 0 and 1 for the second row, and so forth and so on. So that means that I can do 2 times 2 times 2 times 2 different ways of filling in that output column, or 2 to the 4th. Okay. So, and there were 2 inputs, and there were 2 to the 2, or 4 rows, and 2 to the number of rows is the number of ways I can fill in the truth table. So I got 16 possible logic functions, and here they all are. I've listed them all out, from all the outputs being all 0 to the outputs being all 1, and all possible combinations in between. Some of these you'll never meet again in your life. B greater than A is not a logic function that I've ever really used when implementing, you know, a computer. Other of these, like XOR, you'll discover are extremely handy. They're as an essential gate in coming up with a schematic diagram for circuits that do arithmetic. Which of these can we implement as a single CMOS gate? So remember that our requirements for a single CMOS gate is CMOS is a naturally inverting logic family, so rising inputs lead to falling outputs. And vice versa. And so, you know, things like AND gate and OR gates are not something that can be implemented in the single CMOS gate. What I've done here is to circle the ones that I can implement as a single CMOS gate. And in general, what we'd like to do when writing schematic diagrams is, if we can, is to use inverting logic, because then that would, you know, each one of those symbols in my diagram would then correspond to a single CMOS gate. And sum of products, as you've probably noticed, is not full of NANDs and NORs, it's full of ANDs and ORs. And we're going to fix that problem in a second. Okay, so keep in mind that, you know, what the natural logic gate is depends on the logic family that you're implementing. So in CMOS, it's, you know, things like NAND and NOR are sort of and inversions are natural logic gates. It may be that in newer technologies involving carbon nanotubes or quantum computing and things like that, the native logic function may in fact not be AND or NAND or NOR. It may be some other function. And so what we would need to do is we can still use the truth table as our basic building block. But what we would like to do then is to come up with our basic description of functionality. We'd have to come up with a sort of a different mechanism then for translating truth tables into diagrams of the building blocks that come naturally to the logic. And we're going to talk a little bit about that as sort of systematic ways of implementing logic, given sort of different sort of basis functions, different things that are sort of logical. Now, some of you have met Boolean logic before. And so I'm going to give you something to do while I drone on for the next 30 minutes about, some of the other details of designing logic. Okay, suppose we have a logic family where we have lots of ands and ors, but inverters are enormously expensive, $10,000 each. So what I want you to do is to figure out, is it possible to build a combinational circuit that uses as many ands and ors as you want, okay, to construct the inversion of three signals. So this guy takes in three inputs, A, B, and C. The combinational circuit is supposed to produce three outputs, not A, not B, and not C. My question to you is, can you design a logic circuit that implements this using only two actual inverters? Otherwise, you're just using ands and ors. Well, the answer is, in fact, you can do this. It's not obvious. I mean, you're not going to sketch out three gates and say, aha, it's completely clear. Okay, you spend a little while puzzling through to make this work. So it's a little interesting exercise in logic synthesis to figure out if you can get your head around how to do this thing. It does raise some interesting questions. The fact that such a circuit exists does raise some interesting questions. So we can invert three signals using two inverters. And so we have some big circuit diagram that only has two inverters in the middle. Can we actually use two of our pseudo-inverters? So here we have a box that inverts three signals using only two inverters. You can imagine some sort of induction proof about, could we get away with only using two inverters ever? The world would be made up of two inverters and lots of ands and or gates. And the answer is, well, you might be tempted to think that's true, but there's a subtle difference between the circuit that I'm describing here and actually three independent inverters. And it's worth thinking about that. And tomorrow you can ask your recitation instructor, I've thought all night about it and I still don't understand what the subtle difference is. Okay, it's like Homer Simpson thinking that octal is great. You can go ask somebody about that. And so that'll be, you can stump your instructor tomorrow by saying, okay, what is the subtle difference? I'm not going to describe it today. It's fun to think about a little bit. Okay. So you can think about that while we work on some other things. So the question is, what should we actually put into the stock room to build logic with? Do I need, samples of all 16 of those gates I showed you on the previous slide? And what do I do about when I want a 4-input OR gate and all I have is 2-input OR gates? What should I work on? So we're going to tackle that problem next. Okay, so it turns out that AND and OR and NOT are sufficient. They're all we need to do. And so, for example, here's an XOR gate, and I can basically just write that as a sum of products. It has two product terms, not A and B, and A and not B, and you can see I've just wired that up here. And so sum of products is sort of an existence proof that having only AND gates and OR gates and inverters will get the job done. Okay, so, and in fact the XOR gate has this, it has a special schematic symbol that looks like the OR gate, except there's a second back to it, so it's a little double-backed gate here. That's what the second line does. So that's an XOR, the logic symbol for an XOR gate. Here's a different logic equation. You can see this one has a single product term. It's not A and B. And you look at that and say, that's great. What's interesting about that is I could have also designed it this way, with a NOR gate and an inverter. Now, when I say these two circuits are equivalent, what am I actually telling you? They don't look equivalent. They're made of different devices. They have different numbers of transistors in them. What's equivalent about those two circuits? They compute the same function. If I wrote the truth table that told you what the Y output was given all the different combinations of A and B, those two circuits are equivalent. Why might you prefer the bottom one to the top one? If you were, a summer intern and you went off and somebody says, well, the bottom one, why? And you say, oh, I guess I should know why the bottom one is good. Yeah. Right, so what this is this is a single CMOS gate and this is a single CMOS gate. This is actually a NAND gate followed by an inverter in CMOS. So in some sense, this seems more compact. It involves fewer FETs to actually implement. And you look at this and you say, well, it would sure be nice to be able to convert a diagram that looked like this to a diagram that looks like that, and then end up with all this inverting logic, which would be, of course, naturally CMOS. And the answer is yes, we can do that. There is a logic expression here, this equivalence, okay, which allows me to rewrite the top equation as the bottom one. And what we're going to do is a theorem, a theorem in Boolean logic called De Morgan's theorem. And De Morgan's theorem is something that's worth knowing, particularly if you're stuck with a logic family which is naturally inverting. And De Morgan's theorem basically looks like as follows. So the not of ands is exactly the same as the or of nots. That's what De Morgan's theorem is telling me. Right? And you can sort of look at this and you say, oh, okay. So those two things are always equivalent. Notice I've used bubbles to talk about inversions, right? Whenever you see a bubble, think of that as a tiny little part of the circuit that inverts the signal that's going through it, right? So an inverter, which I draw like that, is actually a buffer followed by a little bubble saying, and by the way, the signal gets flipped as it goes through the bubble. So the bubbles are what we use to remind ourselves that things are inverting. So this is a NOR gate. It's an OR gate followed by a bubble. So that's the bubbles and the schematic symbols indicate an inversion that's happening. So what we have is these two equivalents. There's sort of two forms of De Morgan's theorem where I can change an AND gate into a NOR and an OR gate into a NAND, and then I have to worry about somehow inverting the inputs to make the logic equation come out the same. Okay, well, how many different gates do we really need? Here we are. We're running along here, and we sort of say, well, we know we can get away with invert and 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 OR. Can we do something more compact? And the answer is yes. NAND and NOR are what we call universal functions. They're not the only universal functions, but they're the ones that we happen to can build out of CMOS very conveniently. And over here what I've done is I've shown you how to use nothing but AND gates to implement an inverter and an AND gate and an OR gate. Okay, where here's an inverter followed by, and if you can think of this guy, if you use De Morgan's law on this guy, this is the OR of knots, and then the two knots cancel. So the idea here is that if you think of invert and 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 OR as being able to implement anything, I can put in these substitutions and implement any logic function using only NAND gates. And the same thing is true of NOR gates. And so here's the equivalent little diagram showing how to implement each of these guys as NOR gates. And you say, well, boy, those circuits aren't exactly trivial. And maybe I'll just stick with these guys because it looks like NAND and NOR are, even though they're, quote, universal, it looks like gates could be, I have to implement an OR function. It gets expensive. I end up using a lot of gates. Well, so there's two things we want to sort of rummage through. One is, okay, I'm making a big point of this, and you sort of say, well, why bother? It seems like an intellectual curiosity. So in a slide or two, we're going to work on how to build summer products using NANDs and NORs that is much more compact than this translation would suggest. But before I do that, let me talk a little bit about what happens when I want more than two inputs. Suppose I have nothing but two input gates in the stockroom. Can I go off and build a 4-input gate? I have 2 input ANDs. How can I build a 4-input AND? Okay, well, this is, again, is not terribly complicated. None of this is rocket science. I've always wished I was an aeroastro because then I could actually talk about rocket science. And everybody would be impressed, but I'm an EE, so I do these stupid gate tricks. And so the idea, suppose I want an XOR of many things, an XOR of n input signals. Well, one thing I notice is that I can sort of use the associativity. So if I want, A XOR B, so XOR is the plus with a circle in it. XOR C, I can do this as A XOR B and then take the output of that gate, that 2-input gate, and XOR the output of that first gate with the second gate. And I end up with this long chain of gates, like so. And in fact, this does produce, this is a parity calculation, or if you want some modulo 2, of a bunch of signals, this big chain of XOR gates. What's the TPD of that circuit. As the number of inputs grows, as n gets bigger and bigger and bigger, how does the propagation delay of this n input XOR gate grow? Yeah. Well, or linearly. In other words, if I doubled the number of inputs, I would essentially double the propagation delay, right? Because this chain just gets longer. Every time I add an input, I add one more to the chain. So the chain is roughly as long as the number of inputs. As the gentleman pointed out, I mean, there's sort of a -1 in there because the first gate took care of 2 inputs, but all the rest of the gates only take care of 1. Can we compute XOR faster? It's on the next slide, but just think for a moment. What's another way of organizing these things? Okay, so if I had A XOR B, XOR C, XOR D, you could say, well, I could keep doing this and just sort of build it up one at a time. But I could also sort of do them in pairs and build a tree. Okay, so here's a picture. Everybody remember that Joyce Kilmer poem? I think that I shall never see something as lovely as a tree. So you can see it's made a big impression on me. But of course, now it's irrevocably coupled in my mind to this particular slide. An E's view of the universe is sort of strange, I guess. And you can see what we're going to do is that for each layer of the tree, we're doubling the number of inputs that the circuit can handle. Because each time we add a layer to the tree, for every input at the previous end, leaves of the tree, when I add a new layer, for each input, I'm basically doubling the number of inputs that I can accommodate at the next layer. So the number of inputs is growing exponentially as I make the tree deeper and deeper. Alternatively, if I want to think about if I have a certain number of inputs, how many layers of tree do I need? What do I need to do? Yes? Log base 2 of n. So in fact, the TPD of this tree sort of grows as log n. And in general, with 2 input gates, or if it was 3 input gates, it would be log base 3 of n. If it was 7 input gates, it would be log base 7 of n. But there's a sort of logarithmic argument that I can make. Okay, once you tell me how many inputs I'm allowed to do in a single gate, I get this sort of logarithmic effect. So if I want to build a function that looks at all of its inputs, I can't usually do better than a log n TPD. Okay, and the details of the constants of, is it 2 times log n or 3 times log n? So that depends on the details of the complexity of each of the gates here. Okay, can I take, if I want to do the NAND of 57 guys, can I build a tree of NAND gates? Would that work? You can sort of see I can do it with XOR. Now I'm asking the question, suppose I want a 57 input NAND gate. Could I just build a tree of NANDs? No. I agree with no, so explain why no.
I guess I'm just thinking about the idea of a 57 NAND gate would have 1, 0, and then a very large amount of 1. And I guess just logically thinking like 3 ones and a 0 connected together in a bunch of ways.
The pesky thing, so you're zeroing, zooming around sort of what I think of as the right thing. It's the inversion that's getting in the way, right? I can build a tree of AND gates and a tree of OR gates. Positive logic, trees up very nicely. This inverting logic, because each gate inverts, now I'm stuck on the next layer dealing with inversions. And so what happens is the trees get a little bit more complicated to build. If I wanted to build a 57 input NAND gate, maybe what I would do is to build a tree of ANDs and then just put the inversion at the end, and I can build the tree. So thinking about how to do a tree implementation, okay, to get that logarithmic TPD of inverting logic functions, it takes a little bit of thought. And there's different ways to think about it. And in fact, when you get around to designing your beta, which is our 32-bit computer, we're going to need a 32-input NOR gate to do one of the functions that we want to do. And you're going to have to think a little bit about how best to do that. Okay, are trees always best? I mean, we've talked about this trees as somehow having really satisfactory sort of asymptotic behavior. In other words, as the number of inputs grows very large, trees seem to be the best we can do. And the answer is, well, not particularly. We can imagine a different implementation, which is a lot more compact in some ways. Here's a wide fanned-in OR gate. So we can see that what we have here is a resistor pull-up. So if none of these pull-downs is on, then this intermediate node here will be 1 because of the current through the resistor, and then I'll get a 0 out.
Excuse me, Professor.
Yes, sir.
I'm here to deliver a message of love. Is Laura Tequila here?
Aha! In the front row. Wow, this is quite a message. Happy Valentine's Day. It's almost a shame to go back to... Okay, so the question is, when do we stop basically building really wide fan-in gates with stack, either using this sort of tricky technique of getting rid of the pull-up circuit and only putting in the pull-down circuit? This is a static logic, a logic that has some static power dissipation, or just using more and more FETs. And when do we go, when do we do this, and when do we actually go just build a tree of 2 input gates? And the answer is, it's because what happens is every time I add a new input, I'm adding some capacitance, so the gate does start to slow down. This crossover tends to be right around 4 inputs. So the idea is that if you have 4 inputs or less, you just build a big gate to do it. And you have more than 4 inputs, then you start thinking about how to use trees or chains of smaller gates, smaller fan-in gates. Okay. So both of these are implementations of a sum of products. And in fact, the same sum of products we've been dealing with. One is a NAND-NAND tree, and the other is a NOR-NOR tree. You can see the NOR-NOR tree actually involves a lot more inversions. But let's work through, using De Morgan's law, why this is actually equivalent to the sum of products we've seen earlier. And so I'm going to use this notion that a NAND okay, converts into an OR of NOTs. So a NOT of AND, see what I did is I redrew that symbol. You see the little animation there as I change it from a bubble on the output to a bubble on the inputs. And as I do that, as the bubble passes through the body, it converts ANDs to ORs and ORs to ANDs. Okay, so if I take this diagram over here, you can see what I've done is I've redrawn that 3-input NAND gate as a 3-input OR gate with inverting inputs using De Morgan's law. And then I notice I can match up these bubbles. An inversion on the output and an inversion on the input sort of goes away. And now you can see I have my sum of products representation here, but I've built it out of NAND to NAND. So it turns out that if you're dealing with sum of products, you can do it all with very simple inverting logic, NAND, NAND. The same thing is true of the NORs. It seems a little bit more cumbersome to do all this redrawing. And you look at this and you say, well, why would I ever do NOR, NOR? So let me turn this problem over to the collective wisdom of you as budding engineers. Okay, why might I prefer the bottom diagram? You have to think a little bit outside the box to think about why the bottom diagram might be more interesting. Not 100% obvious, but you know, if you were pressed for an answer under threat of having the logarithms come in and sing to you, and said, "Wait, I'll come up with an answer." Really, so you know, what would you do? What would you say? What are some possible advantages of the bottom one? Yes, sir.
Maybe the NOR gate is easier to build or less expensive.
Maybe the NOR gate is easier to build or less expensive. And so the answer is NANDs and NORs actually turn out to have exactly the same number of FETs in them. So that's a good idea. You're sort of on the right track. Yeah? NORs are faster. Well, it depends a little bit on the relative strengths of N's and P's and things like that. But typically each one is fast in one direction and slower than the other one because they have a parallel switches in one for pull up or pull down, and then series switches, and the series ones tend to be a little slower. Okay, but there is something about fast and slow. Yes, sir.
The final inverter kind of lets you control when the output is released.
Yeah. So the idea here is that, you know, notice that to just charge and discharge this output node in this diagram, I have all the FETs. You know, in this case, the pull-down chain for the NAND gate. So all that current has to flow through this little stack of 3 FETs. Here, inverters can be made very fast, okay, because there's only a single FET in the pull-down chain and a single FET in the pull-up chain. And in fact, I can make them wide FETs. And so what I have is the ability to drive very heavily loaded signals with a lot of capacitance. I can make them switch faster. So this idea of buffering in a single signal, a heavily loaded signal, a signal that goes to lots of other inputs, with an inverter is attractive because that way I can make that signal change more quickly by changing the dimensions of the single FETs of the inverter. And so this notion of buffering, here what I'm doing is, you look over here, it's a little easier to see. Here, A is connected to a pair of FETs. Over here, it was actually connected to, you know, these inputs get connected to a lot of different signals. So buffering is something that, you know, is worth keeping in mind. So there are times when, you know, this slightly more complicated circuit would actually operate more quickly. Okay, let's shift gears a little bit. So we've been looking at this function for a long time, and you can see I've shown you 8 different ways to draw the schematic diagram for it. And can I do it with fewer gates? I ended up with a bunch of 3-input AND gates and 1 4-input OR gate, which, you know, maybe I made out of a NAND gate using De Morgan's theorem, or maybe I made it out of a tree of OR gates because I only have 2-input gates. Can I just make something simpler? And so here's a bunch of Boolean algebra identities, okay, that you can use to try to simplify a logic equation. Now, by simplification, what are we after? We're after fewer terms, or terms, fewer product terms, and then we want each product term to involve fewer of the inputs. And if we do so, we're reducing the number of inputs in our gates by somehow shrinking the size of the logic equation. The key Boolean identity we're going to use is what's called reduction. And you can see that in a particular case, if I have a logic equation that's A and B and, just to make sure I'm not A and B, and we think about when is this equation true, the answer is, well, it sort of looks like when B is true, it doesn't matter what A is. So if B is true, B could be a complicated expression. But if the B part of the equation is true, then if I see this in my logic expression, I can reduce this just saying B. Right? Because when B is true, it's true when this expression is true whether A is 0 or 1, so long B was true. Right? So this is a way of doing this sort of simplification. And in fact, you can sort of say, well, it's pretty obscure, Chris. I mean, let's see it in action. And the answer is we're going to use this reduction identity where alpha is any expression and A is a particular literal. We're going to take this guy up here, which is our favorite expression that we seem to have been working on for a while. Okay, and here it is. I've just rewritten it here. Well, I can see here that I have CB and not A and CB and A. This little guy in the middle is a chance to use my reduction and replace that with the single term CB. So you can see I've gone from four product terms, each of which involves 3 inputs, to something now which is only 3 product terms, one of which only involves 2 inputs. My schematic will use simpler gates. And in fact, I can now apply this once more. And I can see I can reduce the original expression, the original sum of products, into a different sum of products, which is using, is now a single 2-input OR gate with 2 input AND gates. And that's sort of neat. You can sort of say, wow, this is actually a lot smaller. So this is what we would call a minimal sum of products. I can't reduce this any farther. There's no more product terms to get rid of. And in fact, you could write a program to do that, these minimization programs. The trouble with the minimization programs is that their complexity, how long they take to run, okay, grows doubly exponential in terms of the number of inputs. And you can sort of say, wow, how bad could that be, Chris? Suppose I have a 100-input equation, right? To exhaustively enumerate all the possible combinations of reductions I could do, to write a program to look for that, I would have to explore a vast number of possibilities, far too many to explore in the lifetime of the universe. So these logic minimization programs are really heuristics. Okay, well, let's talk a little bit about why we want minimal sum of products. Seems to be good because that's the smallest implementation. Okay, so here's the same truth table, and what I'm doing here is showing you a logic diagram. Now, in fact, suppose I have A and B both high, and I have a input. The C input goes from 0 going from 1s to 0. Well, you can see that if A and B are both high, the output is destined to remain high no matter what C is. And we come up to in a situation where it doesn't matter. If A and B are true, the output of this gate will be 1. But with this logic, independently of the value of C, with this logic implementation, though, when I change the value of the C input, because I'm changing which of these AND gates is on, there's a period of time, as C goes from 0 to 1, there's a period of time, and it has to do with the delay of that inverter, when both of the AND gates are off. They're both producing 0, which means that I get this little glitch on the output. And you can sort of say, well, that's okay, Chris. The TPD of this gate is, out here somewhere. And in fact, if I waited for after the C input changed, if I waited for the appropriate TPD, I would in fact get a 1 on the output. In some sense, you shouldn't get all upset about this glitch. And the answer is, well, officially, I'm not upset about the glitch, but that glitch represents, charging and discharging. There's some power supply, some power dissipation things I might want to do. And in general, maybe I want to figure out how to get rid of the glitch at this level. And you'll see in another lecture why getting rid of the glitch for this particular circuit is hugely important. We're going to use it in a very special way. But for now, just think of it as an academic exercise. What I'm going to do is I'm going to add a third AND gate. I'm going to pick 2 more and build another product term out of 2 more sort of rows in the truth table here and build this. This particular implementation involving these 3 product terms is functionally equivalent. The truth table of both of these circuits is the same. Y is the same. The advantage is that this circuit has no glitches when C changes. Okay, and it's removing these glitches, a glitch-free circuit, so that a single change in the input that results in no change in the output is guaranteed to have no glitches, is a circuit that we'll call a lenient circuit. And in fact, you'll talk more about leniency tomorrow in recitation and what it represents. And in terms of truth tables, what we're doing is we're rewriting the truth table to involve these don't cares. We're identifying situations where a particular input doesn't matter, okay, and rewriting the truth table here to sort of eliminate 2 rows here. So, for example, I can take the case in the first 2 rows here. When C is 0, the value of B doesn't matter, right? So I've sort of rewritten that. These first 4 rows I've rewritten as just 2 rows with a don't cares. So the don't cares are sort of useful to us because they will allow us to implement more compact logic. And in fact, for recitation next Wednesday, we're going to talk about a systematic way of finding don't cares and using them to your advantage to implement minimal sum of products implementations. Well, this truth table that we've been working on all day represents a circuit that we call a multiplexer. This is a 2-to-1 multiplexer. It takes 2 signals and chooses one of them to be the output signal. So that's given, we call that a multiplexer. It has a select line that selects which of the 2 inputs. So it has 2 inputs and a 1 output. Here's a 4-to-1 multiplexer where I have 4 inputs and I need 2 select signals to select which one of the 4 signals will become the output. I see that down here. And in fact, I can implement a 4-to-1 multiplexer just as a little tree of 2-to-1 multiplexers. Now, multiplexers will be really handy, and let me show you one way in which they're handy. Suppose here's an 8-to-1 multiplexer with 3 select signals, and I have an arbitrary logic function here. I've sort of randomly written a bunch of 1s and 0s in the output column. It turns out by using this multiplexer, I can implement any logic function I want simply by wiring the inputs to the appropriate constant 0s and 1s. Okay, and I'm going to select the appropriate row. You can see the 0s and 1s I've chosen are exactly the truth table. What I've done is I could implement any 3-input Boolean equation using this 8-to-1 multiplexer and simply changing the wiring to constants on the input. So this is an extremely systematic way of implementing logic. I can design this circuit and simply change whether I put the inputs, hook the inputs to power or ground. Okay, and by doing so, I can implement any logic function I want, any 3-input logic function I want. So these multiplexers give us a very systematic way of implementing sort of arbitrary truth tables without having to go through all the complexity of building, sum of products and wiring up gates and wondering if I could do with less. I'm paying the complete cost. In other words, I have enough logic to implement every possible Boolean function built into this. Having paid that cost, I get ease of implementation. Okay, so in general, this notion of a lookup table synthesis, yes?
I'm not sure I understand how a multiplexer lets you...
Okay, so the multiplexer is going to select one of those inputs, right? So when all 3 of these signals is 0, it's going to select the 0 input. If these signals were 1, 0, 1, it would select, the 5th input, so forth and so on. Does that make sense? In other words, the multiplexer, the definition of a multiplexer is it chooses one of its inputs to be the output value. So what we're doing is we're using the variables that come into the equation, A, B, and C, okay, as the things that will select which one of these things will become the output. Okay, and so what we're doing is we're saying, think of this as rows of the truth table. We're selecting which row of the truth table to look up the answer. And we've pre-programmed that particular line, that particular input, to have that, whatever the value was in that row of the truth table. So this is a systematic way of implementing a general purpose truth table, and we can change the truth table we implement simply by changing the 0s and 1s on the inputs. I'm putting in a lookup table. Now, in fact, there's a whole type of logic family called a field programmable gate array, which in fact implements actually these general purpose muxes. And what you're changing when you program the field programmable gate array to implement different logic functions is you're changing the 0s and 1s that are wired to the inputs of the mux. In general, for an n input function, I need a 2 to the n input mux. And so this gets quite expensive for big logic. On the other hand, here's an example of why muxes are universal. And in fact, think about what this is a logic gate, which normally takes about 10 FETs to implement, but which implement quite compactly here in this mux. Things like carbon nanotubes, which are, everybody's sort of hot on these days as a possible way of building pretty neat, very, very, almost molecular slice logic. Okay, I think they naturally implement a multiplexer as the thing that they do quite well. So, okay, So what I'm going to do is I'm going to stop here in section on next Wednesday. We'll spend some time here talking about generalizing the sort of lookup idea to build memories that allow us to sort of look up the answer, so-called read-only memories. So remember, there's no lecture next Tuesday, right? Because Monday's President's Day, the holiday. The Institute is running on a Monday schedule next Tuesday. We don't meet on Monday, so we won't meet it. So the next time I'll see you is a week from today. But you have 2 recitations between now and then. Good luck on Lab 1.